Hello, welcome to another module in this massive open online course. So, we are looking at the Fourier analysis and we are looking at example problems in the Fourier analysis, and so far we focused on example problems for discrete time signals. Let us now shift our focus to example problems for continuous time signals. Okay. So, starting this module we are going to look at again example problems for the Fourier analysis. And this time specifically focusing on your continuous time signals, the CT or continuous time signals. Okay. Let us start with example, continuing our example numbers. Let us start with example number 6. Let us consider a very simple yet fundamental signal, and this we will encounter in various applications. That is, let us say I have a signal, a rudimentary, a very basic signal that looks something like this, it is a pulse, continuous time signals and aperiodic. Remember, we have looked at so far, we have looked at continuous aperiodic signal, periodic signals. So, the Fourier series. Let us look at now continuous aperiodic signals. Okay. So, this is a pulse, a rectangular pulse if you will. So, this is a rectangular pulse of width t. So, from minus t by 2 to t by 2 of height unity. This is in time domain, this is the signal x t. We denote this as the pulse x t equals p t, pulse of width t of t, p t of t, which to define it formally, that is denoted by pulse of width t. This is basically 1 for magnitude of t less than or equal to capital T over 2, and this is 0 otherwise. And this is pulse of width t, pulse of height unity width t centered at 0. So, the way to think about is pulse of width equal to t, height equals unity, and this is centered at 0. Okay. Now, we want to find the Fourier transform of this. So, P t of t, let us denote this Fourier transform by capital P t of omega, that is the Fourier transform of this pulse. And remember the expression for the Fourier transform, the continuous time Fourier transform, that is your integral minus infinity to infinity p t of t e raised to minus j omega t dt, which is basically non-zero only from minus t by 2 to t by 2. So, I can write this as this becomes your integral minus t by 2 to t by 2, which is 1 in this range. So, it is simply e raised to minus j omega t dt, and taking the integral, this will be e raised to minus j omega t divided by minus e raised to minus j omega t divided by minus j omega between the limits, obviously between the limits minus t by 2 to t by 2. So, this integral is e raised to minus j omega t divided by minus j omega evaluated between the limits minus t by 2 to t by 2. Now, substituting the limits, we have e raised to minus j omega t by 2 minus e raised to j omega t by 2 divided by minus j omega, and we know that e raised to minus j omega t by 2 minus e raised to j omega t by 2 t over 2 is basically sin omega or 2 j sin omega t over 2. Okay. So, I can simplify this as 2 j using the properties of complex numbers, that is e raised to minus j theta minus e raised to j theta. Okay. So, 2 j sin omega t by 2 by, in fact this is minus 2 j sin omega t by 2 by minus j omega, which is basically, you can simplify this by cancel. So, this will be sin omega t by 2 divided by, or twice sin omega t by 2 divided by omega, and this you can, this is your Pt omega, that is the Fourier transform of this pulse, and you can multiply and divide by t over 2. So, this is twice t over 2 sin omega t by 2 divided by omega t over 2, which is equal to t sin omega t over 2 divided by omega t over 2. And further, I can also write this as, remember we are still simplifying the same expression, I can write this as t sin pi omega t over 2 pi times pi omega t over 2 pi, and we will now define a notation. This is a popular notation, this is known as the sinc function, sinc of x or sinc of u equals sin pi u divided by pi u. So, this is known as the sinc function, and it is one of the most a very convenient and very frequently, something that is very convenient use and something that arises very frequently in communications and signal processing and in general in signals and systems. So, this is termed as the sinc. This is the sinc function, and therefore, this here will simply be t sinc omega t over 2 pi or t sinc of omega t over 2 pi, and this is your Pt of omega. And further, if you denote omega over 2 pi as omega is an angular frequency, omega over 2 pi is the frequency f, then this simply becomes t sinc ft. So, substituting omega over 2 pi equals f, you can write Pt, that is the Fourier transform in terms of the frequency Pt of f, this will be equal to t sinc of ft. Or t sinc of omega t over 2 pi. And if you plot this t sinc omega t over 2 pi, equals t sin omega t over 2 divided by omega t over 2, and you can see that sin omega t over 2 sin omega or sin omega t over 2. Now this is 0 if the numerator is 0 if omega t over 2 equals k pi implies omega equals omega equals 2 k pi over t. So, this is 0 for omega equals, for instance, minus 2 pi by t, 0, 2 pi by t and so on, 4 pi by t and so on. Okay. And as limit, remember limit omega tends to 0, you can check this, sin omega t by 2 by omega t by 2, this is equal to t. So, at t equal to 0, this is t. Okay. So, this t sinc omega t over 2 pi, at omega equal to 0, this is t, this has magnitude t, and it is 0 at every integer multiple of, that is 2 k pi over t, where t is the width of the pulse, at every integer multiple of 2 pi over t. Okay. And you can see that the amplitude of this is decreasing, this is amplitude is decreasing as t over omega. So, if you look at the envelope of this is something interesting, envelope which is places where the sign has magnitude 1. So, that will be t over omega t over 2, which is basically equal to twice over omega. So, this is linearly, so it is decreasing in omega, linearly decreasing in omega, or not linearly, this is decreasing inversely in omega. And with that we can plot this. So, if I try to plot this, so this will be something which is of height t with a decreasing envelope, and these points, so this is t, and these points where it is 0 are 2 pi by t. So, at 0 it is t, this point will be 4 pi by t and so on, this is on the omega axis, and this point will again be minus 2 pi by t minus 4 pi over t and so on, and this is your sinc function, sinc of omega t over 2 pi times t, and this is equal to your pt of omega. Okay. And this is what we know as sinc function, and if you can see, the envelope is something that is decreasing. The envelope is decreasing as 2 over omega, something that is decreasing, that is as omega tends to infinity, the signal or the response of the signal, right, the Fourier transform tends to 0. Okay. And this is important, as I said, because it arises in a large number of applications related to communication and signal processing, because the pulse, the square pulse itself is something that is very fundamental to several applications. Okay. Now, let us look at something interesting, which is we look at what is the, now we have seen the Fourier transform of the sinc pulse. Now, let us look at the inverse Fourier transform of the sinc pulse. So, or let us look at, we have looked at the Fourier transform of a square pulse, let us look at the Fourier transform of sinc pulse. And needless to say, we can use the duality principle. That is, what we want to do is we want to consider a signal xt which is sinc of alpha t, which is basically sin pi alpha t over pi alpha t, and we want to ask the question, what is the Fourier transform of this sinc pulse. Now, the Fourier transform of this sinc pulse we can use the duality principle. Naturally, we know that the Fourier transform of the square pulse is the sinc in the frequency domain. So, using duality you can already see, if you look at the sinc pulse in the time domain, its Fourier transform must be related to that of a square pulse in the frequency domain, alright. So, we use the duality principle, alright, which states that if xt has Fourier transform x of omega, then capital Xt, that is capital X of t, must have Fourier transform, we have already seen this, 2 pi x of minus omega. This follows from the duality principle. So, now we have Pt, remember from the previous problem, Ptt has the Fourier transform t sinc omega t over 2 pi. Now, using duality it follows that if I replace omega by t, that is t sinc t times t divided by 2 pi, this has the Fourier transform p of t or 2 pi, this has the Fourier transform 2 pi p t of minus omega. Now, look at this, the pulse, right, the pulse is an even function, correct. We have seen that the pulse is centered at 0 and it is symmetric about 0. So, Pt of minus omega is the same as Pt of omega. So, this is equal to twice 2 pi Pt of omega, since pulse is an even function, since your square pulse is a, since Pt of omega equals is an even function, okay. And this implies that if you look at sinc t times t by 2 pi, that has the Fourier transform, if you could take to the t to the other side, that has the Fourier transform 2 pi over t Pt omega. Now, set t over 2 pi equals alpha implies t equals 2 pi alpha, and therefore, from here you will have sinc of alpha t has the Fourier transform which is 2 pi over t. So, this will be your, I am sorry, I am setting t over 2 pi equals alpha. So, this will be t equals, so you will have 2 pi over t will be 2 pi over 2 pi alpha, and p of t is 2 pi alpha omega, which is nothing but p of 2 pi alpha divided by alpha. Now, if you look at 2p of 2 pi alpha, that is nothing but pulse of width 2 pi alpha centered at 0 and height 1, and now you have 1 over alpha times that. So, the height will be 1 over alpha. So, it is a pulse, so 1 over alpha, p 2 pi alpha omega is a height, is a pulse of height 1 over alpha in the frequency domain centered at 0 and of width 2 pi alpha. Therefore, it spans from minus pi alpha to pi alpha, okay. So, therefore, this will be, if you realize that, you can see this is pulse of width 2 pi alpha, height equals 1 over alpha, centered at 0. So, therefore, this is going to be something that is that looks like this, okay. I am just going to draw it. Okay. This is from minus pi alpha to pi alpha, height 1 over alpha, and this is your p of 2 pi alpha 1 over alpha, and this is the Fourier transform that is of alpha. This is the Fourier transform of Sinc alpha t. So, Sinc alpha t, which is what we set out to find the Fourier transform of, has the Fourier transform 1 over alpha p 2 pi alpha p 2 pi alpha omega, and therefore, this also implies that if you bring alpha to the left hand side, alpha Sinc alpha t has the Fourier transform p 2 pi alpha times omega. Okay. So, that is basically what we have over here, and another simple manipulation, if you look at so if you set alpha equals, and if you set alpha equals a over pi, this gives a over pi Sinc a over pi t is your p of 2 pi alpha, alpha equals a over pi. So, this is p of 2a omega. Now, remember Sinc of x is sine of pi x divided by pi x. So, this will be your this implies that a over pi times sine pi a over pi t, that is sine a t, divided by pi a over pi t, that is sine of pi a. So, that is a t, that has the Fourier transform p of 2a of omega, which implies that now you have the a is cancelling. So, sine a t by t, or which implies that sine a t by pi t has the Fourier transform, that is p of 2a of omega. So, sine of pi t by pi a t, and this is basically, you can see this is pi pulse of height 1 width 2a. This is your p of 2a of omega. Okay, and this has a, so sine a t over pi t has a Fourier transform p of 2a omega, which is the pulse of width 2a, okay, that is from minus a centered at 0 from minus a to a, and of height 1 in the frequency domain, in the angular frequency domain, omega domain. All right. So, we will stop here and continue with other problems in the Fourier analysis for continuous time signals in the subsequent modules. Thank you very much.